Okay, so MGF of Poisson, we know the PMF. That's the standard Poisson distribution. Instead of lambda t, which we did in class, I simply used lambda because I don't want you guys to get confused between that t and this t. Too many t's. So that is the PMF. So the moment generating function is simply the expectation of e raised xt. Which would be k equals 0 to infinity e raised kt times lambda raised k e raised negative lambda divided by k factorial.
Or is that also supposed to be the power?
It's a power, I'm sorry, e raised k. It's in the power. So e raised negative lambda is the constant, so I can pull that out. And I have e raised kt, lambda raised k, divided by k factorial. I can use Taylor series of an exponential if I do something over here. I can combine these together, yes, because they have a common exponent. So I can write it as lambda e raised t raised k divided by k factorial. Yes, properties of exponents. What would that produce to? We did this at the beginning of class.
Into the contrary.
This is nothing but e raised lambda et, because that is simply the Taylor series expansion of e raised x evaluated at lambda e raised t. So if you call that x, you will see that is simply the Taylor series of an exponential function. So we would end up getting e raised lambda e raised t. If we combine the two, I'll have e raised negative lambda 1 minus e raised t. Good. The moment generating function is a function of t. You should not forget that. We have a new variable t. The support depends on the variable t and where this function exists. So another common mistake that I've seen students make is to call the support of the moment generating function to be the same as the support of the random variable. They are not. This is a function of t, therefore the support of the moment generating function is defined where t exists. That makes sense. So we're going to find the first, second moment. First derivative. So that is my function. Taking the derivative with respect to t. So I have a function of a function. If I treat whatever that I have in the power as just x, so the derivative would simply be e raised negative lambda times 1 minus e raised t multiplied by the derivative of that chain rule. So minus lambda, derivative of 1 is 0, derivative of negative e raised t is negative e raised t. So we would end up having lambda e raised t times e raised minus lambda 1 minus e raised t. If I plug in t equals 0, lambda e raised 0 times e raised minus lambda 1 minus e raised 0. E raised 0 is 1, 1 minus 1, 0. E raised 0 is 1, 1 times 1 is 1. So we have lambda. Off to the second moment. We simply have to take the derivative of that. I can show you this product rule, but I'm going to rewrite it in a different way. Easier. Take the derivative, so lambda e raised t minus lambda 1 minus e raised t multiplied by the derivative of t is 1. The derivative of lambda is 0. Derivative here is lambda e raised t. Yes. Now I have to evaluate the moment generating function at t equals 0. Lambda e raised 0 minus lambda 1 minus e raised 0, which is 1 minus 1 times 1 plus lambda e raised 0. All of that is going to become 1. So we would end up having lambda times lambda plus 1. And from this, of course, we could find the variance. So the variance would simply be this term minus the mean squared. So minus lambda squared would simply end up giving lambda. We know the variance of a Poisson distribution is lambda, the mean is lambda. We did derive this, right, when we did Poisson. Now, we went through this entire process to find the second moment. And sometimes we had to use certain tricks, geometric, for instance. We weren't able to find the moment directly, so we had to take derivatives and then find the moment. But if you spend the time to find the moment generating function, that is all you need, and everything will just fall in place. Clear? So MGF, and as Nathan mentioned, this is closely related to Fourier transforms. And you may ask, well, why is that important? Earlier, sums of random variables, when we had that, we were able to write it as a product of moment generating functions, which is very important because sums of random variables come in statistics all the time. Good.